right. So, good morning, good afternoon, good evening. Where are you joining us from? Welcome. So, on behalf of the SP MENA Hydrogen Technical Section Working Group, it's a pleasure to have you with us for today's technical webinar. If this is your first time attending, we're thrilled to have you on board. And we'd just like to begin by saying that our working group is committed to advancing conversation around hydrogen, especially in technologies and emerging trends. And we also look at fostering collaborations across the energy sector in the MENA region. We usually explore critical areas like hydrogen production, storage, integration, and the broader role hydrogen plays in accelerating the global energy transition. And today, we are especially excited to welcome Ms. Swati Gupta, founder of Rara Energy, as our distinguished speaker. So Swati brings over 2 decades of deep expertise in the oil and gas industry with a strong foundation in reservoir engineering, storage projects, planning, simulations, and her work also spans across major basins across the UK, Africa, India, and now she's leading innovative efforts in hydrogen storage and CCUS. She's known for bridging traditional energy with future of renewables, and there's a lot I believe Swati can also add on in terms of her expertise. But with that said, this promises to be a thought-provoking and insightful session, and we are grateful to have Swati be on board with us, share her knowledge and her expertise. And before we begin, I just wanted to say this webinar is a part of our ongoing series, so please stay tuned for more exciting discussion from the SP MENA Hydrogen Working Group. And we would also be having a few announcements around EDIPEC. If you are in town for EDIPEC, please feel free to connect with us. And we will have a detailed presentation for around 40 minutes, followed by a Q&A. So with that high-level agenda set, let's dive in. Swati, over to you.
Thanks, Abhijit. Thank you, SP MENA section, and thank you, SPE, specifically Suhail, Abhijit, Karthik, Magdi, and the team for giving me this opportunity to share my insights, some of the work I recently did. And thanks, Abhi, for the warm introduction. I just wanted to add to what you have already said on my storage experience, underground natural gas experience that I've worked on several major projects, including Rough Field, Baines and Baird Field. They're all part of North Sea and UK onshore. As well as I've worked on some of the CO2 storage developments in the last few years as part of Rara Energy, but before as part of other companies I've worked for. And later, obviously, I've become involved in a unique hydrogen storage project about which we will be talking today, which is basically taking the hydrogen from a green hydrogen plant, well, mostly green, and storing it somewhere in the depleted field. And I will be talking about the feasibility work we did. So yeah, thank you very much for joining. I will move. Just to check, can everybody hear me? Okay.
Perfect.
Yes.
Great. Thank you. So I will be talking about some of the fundamentals and global momentum using some of the recent Stats Hydrogen Council report. We will then delve into some basics of hydrogen, types of hydrogen, industrial use of hydrogen, and how we can produce, not going too much deep, really high level, and then deeper into the storage solutions and what challenges we are facing today and why underground hydrogen storage is important. And then from that, I will take you to the study which I performed and in which I'm writing a paper as well in EDIPEC. And then we will be having Q&A and discussions. So hydrogen fundamentals are quite important. I think hydrogen has been in the news recently, but actually it's been around for a long time because of the industrial use of hydrogen. But obviously now that it is being advertised more as a zero carbon energy carrier, it is the fuel of the future. That is why there's more talk about it. As the lightest element, it is approximately 8 times lighter than methane. So don't want to talk numbers here, but it is a lighter molecule, as we all know, first in the periodic table. Hydrogen can also be produced from a variety of sources, so including renewable energy, which is what is being talked about so much now. And it plays a very crucial role in obviously the carbon emissions, because it could be replacement of the fossil fuel and the issues we are facing from the fossil fuel burning. But we will talk also about why hydrogen still can be used using some of the gas projects, which is then the blue hydrogen, and we'll talk about that. And furthermore, the hydrogen will offer versatile applications as well, ranging from heavy industry, transportation, power generation, which actually makes hydrogen a key component in the transition to the sustainable energy. So the global stats is basically, this is from the latest Hydrogen Council report, which is released recently in 2025. I think it was August or September. And that says it's about, so 110 billion plus is already committed to clean hydrogen projects. Now, the report actually talks about clean hydrogen. And if you look deeper into that report, clean hydrogen is a mix of renewable energy, renewable hydrogen, which is what they're calling it, green hydrogen. They're actually calling it renewable hydrogen for some reason. And then obviously the other part is the blue hydrogen, which is then called low carbon hydrogen. And that is basically using still the fossil fuel, but doing the CCUS. So there's a lot of investment basically committed by 2030. Why 2030? Because most of the countries have got a net zero by 2030. So it's we're already in 2025, so we're not far. And with the 500 plus projects at FID under construction or operating. And this report is actually quite interesting. So I suggest everybody to go through who is interested more about hydrogen. 6 million tons of capacity, and out of that 1 million ton is already online. So that is some achievement there. And there are about 50 plus projects which are cancelled or postponed, which is important to note here. And why that is there is because of the market policy, and we can again cover that in the Q&A more. And if you look at on the right side, China is really leading the figure here. North America, I mean, the notion would be that it is Europe where hydrogen is being driven. But actually, you can see North America and Europe. There is a lot of commitment, but the new commitment is coming from a lot from China, India, Middle East, and the other countries, which are actually, some of them are developing countries. So positioned as a key exporter, European demand is driving definitely the renewable hydrogen. And the idea is really the natural gas is supporting the low carbon exports. So natural gas is still needed. So basically, the key takeaway from here is that gas and oil and gas are there to stay, and gas is actually a key element for hydrogen. Now, major hydrogen projects, where are they located? So globally, so this is again from the same report, and it is showing all the colors here, and you can see the blue color is the gigascale production. The lighter ones are, so it's all depending upon the size of the projects. You can see the biggest sizes are probably mostly in Europe. Some are in Africa, actually. Some of the really large plants are in Africa. So since 2020, the global hydrogen project has grown almost sevenfold, signaling a very strong momentum in the clean energy development, with obviously Europe leading with almost 200 post-FID projects, so been already done, focused on green hydrogen and supply chain integration. And such as there are some examples like High Deal Ambition project. They are aiming to supply, low-cost hydrogen. Then China is now becoming the top investor, pouring billions into a mega-scale renewable hydrogen projects. So this is all renewable hydrogen. So again, you'll see that sort of terminology used in sport, which is basically using solar facilities like Inner Mongolia green hydrogen plant, and that is going to work for their national strategy, national energy export goals. And so you see that as a result, Europe's global share is actually dropping down to around 40%. That's what the report talks about, with the rapid growth in North America and Latin America, like Chile's. There is a plant in Chile, which is quite popular. And some of the plants in actually MENA region, led by Saudi's NEOM green hydrogen project. So this actually marks quite a clear global shift in the hydrogen investment and the outlook. So what are we looking at in terms of capacity? So how much is the clean hydrogen projects? What is it looking like? So we obviously, hydrogen and CCUS, we talk about tons. Then those who are from the oil and gas industry, we are used to more on the cubic feet or barrels. So that's now tons, because this is how hydrogen is being measured. And what we can see in the North America, 2.4 million tons. Out of that, Europe is doing 0.3. So you can see it's very heavy in terms of total number of capacity. So like a very high amount of hydrogen is being stored here. Europe is 0.3. And if we combine the Middle East, it's 0.3. And then the 1.4 from China. Now, these projects are clean hydrogen, as they call it, feed plus projects. Okay, what is feed plus? After the front-end engineering design is completed, which basically shows that most of them could be going into the online, and we don't know, but quite a high chance. So the clean hydrogen market is seeing its first wave of mature projects, and with FID under construction, operational, and the investment is almost surpassed about 110 billion across 510 projects. So that's the stats. Almost up 35 billion from last year, with over 50% annual growth. So it's pretty significant. 50% annual growth since 2020. So in 5 years, there's a big progress. There's a very good progress. So stronger projects obviously are moving forward, while the weaker ones, where the economics did not work, are dropping down. And on the supply side, about 1 million ton of hydrogen is already operational out of 6. So yes, we are slow, but we are getting there. By 2030, the pipeline of projects could support about 9 to 14 million tons. It is ambitious, but it is what is expected, depending upon how much, obviously, the new capacity secures the commitments, and how it goes from here. The demand heavily depends upon the policy, obviously, and the offtake agreement. So remember that this is all very much dependent upon the market and the demand. So that was just a very brief introduction from the sort of stats from the council report. Now we're going to move to different types of hydrogen. I think most of us would know, but just to sort of give a little flavor of different colors here. Gray is the steam reforming of natural gas, which is the most common and the cheapest, and it's produced from natural gas through steam reforming, but it emits high level of CO2 because it's using natural gas burning. Blue is also exactly the same, but we capture the carbon using the CCUS, and it's also called as low carbon hydrogen generally. Green is the sort of electrolysis using renewable energy, and there's no emission, true clean energy source. Either it has to be solar, wind, or any kind of renewable energy, it doesn't matter. The production cost is high. Why? Because the renewable energy cost is dependent upon that. So that is why it's high. Black and brown, gasification of coal, very harmful. And then we go to pink, which is nuclear energy, which is also referred to as purple or red hydrogen. And then turquoise, methane pyrolysis, and that's emerging now, emitting no CO2 and producing solid carbon. And last but not the least, gold hydrogen or white hydrogen, which probably you've been talking about a lot, which you've been hearing. That is a geological hydrogen, does not require production from fossil fuels, and but extracting of that hydrogen will still require some form of energy, and if it is fossil fuel, then it is not really the no zero carbon emission. And there was a news in huge reserves in France, which have been making this news for the geological hydrogen. Many universities are working on this. Okay, which basically takes us to some of the storage challenges here. Why are we talking about hydrogen storage, and why is it important in the whole value chain? The hydrogen is when it will become the fuel of the future, it is very important to understand that it will have the subsurface, surface, and the regulatory market challenges, because it will be a fuel which will be then stored, and then it will have its own challenges on the surface, infrastructure, and the regulatory market. So we will touch upon this slide a little bit later. Let me go to the sorry, I'm just going to look at. Okay, sorry. I think there is some mismatch of my slides here and there, so I'm just going to go to the industrial use of hydrogen first. So from the hydrogen, we understood that it is a fuel which has been used in many sectors, and it plays a vital role in several major manufacturing industrial processes. In ammonia production, it serves as a key feedstock for the fertilizer. So that's why you hear a lot about the ammonia production, and now ammonia becoming a fuel because for some of the shipping industry, and there is a lot of research going on. This is all an active area of research, by the way, when obviously the economy will be dependent upon hydrogen. That's the assumption. So there's a lot of work being going on. But saying that, ammonia is still used for fertilizer production. So that's the main industry. Then again, methanol production, hydrogen is combined with the carbon monoxide and it could be carbon dioxide, and then it is then used for methanol to produce methanol, so which is a versatile chemical used for manufacturing of different acids and biodiesel and things like that. And then in the refining industry, hydrogen is also used to remove sulfur and a called desulfurization process. And actually, it just basically takes out the sulfur impurities from fuels such as diesel and gasoline, and help produce a little cleaner fuel. So that is how hydrogen has been used in the past. The low carbon hydrogen obviously is a slightly newer industry, and it is increasingly being adopted for various sectors like automotive industry and fuel cell industry, and probably hearing more about that testing of the hydrogen fuel cells. And why is it? Because if you use a fuel cell powered car, it will only emit water vapor, offering a zero emission alternative to the conventional vehicle where there's a high emission. For example, there is a hydrogen fueling stations. We've been seeing that hydrogen buses are planned to be start in Abu Dhabi as well at the end of 2025. I'm not sure how that project is going ahead, but there was a lot of announcement on that. And for example, the Toyota another car, Toyota Mirai, is something which is running on hydrogen fuel cell. Mostly in every conference where you go to sustainability, you will find these examples of hydrogen fuel cell, and there's you will see a lot more sort of usage of fuel cell. But again, it's very expensive. Still needs to be scaled up and compete with the traditional fossil fuel. So it's early stages, but it's the future. Now, just a quick one on producing low carbon hydrogen. I'm not an expert in this, but the production of low carbon hydrogen, we are talking about using the electrolysis. We are not talking about traditional hydrogen production, but we'll talk about the electrolysis of water, which is what is a very energy intensive process. The water is split into hydrogen and oxygen using renewable energy electricity, using wind, solar, and hydro. And basically, we are splitting the water, and it's fully sustainable, zero carbon emissions, and different types within the electrolysis. We are using alkaline electrolysis, proton exchange membrane, and solid oxide electrolysis cells. And there's again area of active research in terms of reducing the cost of electrolyzers. Over the last few years, electrolyzer costs have gone sort of almost 50%, reduced by 50% because of the technology spending on technology advancements. Then hydrogen can also be low carbon hydrogen can also be generated by biomass gasification. So what do we do there? We take the organic materials which are converted then into hydrogen through using the heat and oxygen, and produce minimum CO2 if obviously sustainably sourced, depending upon where the electricity is coming from. So that can also be an advantage to make the carbon neutral if we are sourcing the electricity. So I guess the key here is the source of electricity or the source of energy. Then another one is the thermochemical water splitting. Again, we are splitting the water, but using high temperature processes. Solar or nuclear heat, and we still that is, again, it uses very high temperature processes, so very high amount of electricity and energy costs is there. Still experimental, but it's also something we are looking at. Now we have moved to surface hydrogen storage solutions. And we will be, so what are the different options here? So in terms of the surface, just like oil and gas, the question is why we cannot store it on the surface. So yes, you can still store hydrogen at the surface, and these are the solutions, but we will take you to details of why we cannot, that is not feasible and very costly. So compressed gas tanks have been used, which are pressurized hydrogen stored in the pressurized vessels. They are common in mobility and small scale industrial use. Then the hydrogen is also stored in cryogenic temperatures, which is a higher energy density that provides an ideal for aerospace and long range transport. Now we will talk more about why liquid hydrogen is needed. So just like LNG, we can do LH2 here, but it requires very, very low temperatures, which actually it's not available yet, the cryogenic temperatures, because it's really low. Then another form of storage is liquid organic hydrogen carrier, LOHCs. And what happens there is the hydrogen is chemically bonded to some of the organic liquids. They are easier to handle, but again, they require energy for release. So not really that much of energy conservation there. Now, hydrogen is a very reactive molecule, right? I mean, hydrogen is part of all the molecules we are using, all the compounds we are using. So it can be attached, stored in some solid metal lattices, because it can attach very easily with the metals. So that could be another way, another safe way to store hydrogen. But what will happen is that, the kinetics and the higher weight is an issue. But you can see there's complex hydrides, metallic hydrides, physically absorbed hydrogen, which is what will be used. So in general, what are we looking at in terms of challenges here in terms of hydrogen storage? Because this webinar is about storage. We will talk more about that. I'm not sure if you can clearly see this chart, but what we are showing here, that hydrogen has 3 times the energy by weight of gasoline, or 1 kilogram of hydrogen is about the same energy as 1 gallon of gas. So on the right side, what do we see? We see that we are starting at gasoline as here. Sorry, please, can we mute? Someone is actually not muted. Thank you. So we start with gasoline, diesel, compressed propane, and then we are looking at natural gas, LNG, cooled liquid hydrogen, and compressed hydrogen here. So what do we see? The chart is showing on the x-axis is energy content per volume and energy content per unit, weight. So this is weight, this is volume, and you can see the hydrogen does come very low on the volume, and that's why it is being talked about the energy density, that it has very low energy density, but it is actually high in terms of energy per weight. But what we want is volume, because we are looking for the storage here. And that is why, to be honest, hydrogen has not been used as a fuel, even though hydrogen actually is the calorific value is quite good. So the hydrogen low energy by volume is one of the main barriers here in the industry. What other issues are there for storage is that the energy, because of the low density, energy density, it can be compressed only at high pressures or converted into liquid at low, both of which will require quite a lot of energy, right? And strong and costly equipment to be able to then store and compress. Material compatibility is another issue. Hydrogen can cause embrittlement in certain metals because of the reactive nature, and it can lead to structural weaknesses, especially for steel. And most of our storage tanks and pipelines have been made with steel, so that could be an issue. This necessitates use of specialized materials, and you have to use composites, and composites can be quite costly. In terms of storage duration, the hydrogen storage solutions will be accommodate varying time frames. So we would require sometimes short-term storage for immediate use to long-term storage for seasonal energy. And you will see in the case study that we'll talk about that. And in terms of safety concerns, hydrogen is highly flammable and requires stringent safety measures for storage facilities. So ensuring the systems is crucial. So this is the beginning of hydrogen, underground hydrogen storage. So one of the solutions offered is storing hydrogen in underground. Why? Because of the issues we talked about before, the energy density, low energy density, because there is so much space in the porous rocks and subsurface salt caverns. So again, this is an area of still active research. There are not many commercial solutions available, but there have been a lot of examples in UK, US, and Germany where they have proven this technology is still very new. Salt caverns are the artificial cavities within the salt domes, and you have to mine them to create them. These are called non-porous storage, and they don't come with the issues of porous rock storage we'll talk about. So what happens in the porous rock storage? Porous rock storage will have three main things of depleted gas fields, aquifers, and depleted oil fields as well. What happens there once we have emptied the oil and gas? The porous rock is able to store safely, because oil and gas have been there for ages. It is a very similar experience that we have from the natural gas storage mainly used in Europe for the balancing of energy balancing. In terms of aquifer, they are normally deep aquifers. So the CCUS industry has been still testing whether you can store the CCUS, although it's slightly different. Hydrogen storage and CCUS are different. But we have been looking at porous rock formations containing water. They are cost effective, but they are very experimental. Why? Because we don't have the data set there. So in terms of different storage sites, salt cavern will be medium capacity. It requires low cushion gas. We did not really talk much about cushion gas, but cushion gas is required to maintain the pressure. And that is something which we will not be using. So we need to put cushion gas. It's almost like a CapEx investment into any storage project. The capex is very high for salt caverns. Why? Because it needs to be mined first, and mining requires a lot of water. So not necessarily green, because you need to use high energy to actually mine it first, and then you will have to use it, the cavern, which is not created. So you have to create a cavern first and then use it. This maturity, it is proven, and the availability could be a site availability could be a risk. In terms of depleted field, it is the capacity is very high, so it is normally used for. It is recommended for the seasonal high storage rather than the quick storage. I will talk about a little bit later. Cushion gas will be medium, not as much as aquifers, but capex will again be medium, depending upon depending upon how many wells, what is the facility, where are we onshore, offshore, everything. But then there are quite a lot of risks. We'll talk about that as well, which come with that. This is emerging maturity, because we don't have a lot of examples there. And then the aquifer storage, where the capacity is quite high, because aquifers are actually very large. Cushion gas will be high there because they are not pressurized, just like oil and gas. The capex will be similar to depleted fields. Still have to drill the wells, facilities, things like that. But the maturity is low because we have not done any hydrogen storage in aquifers, and it's probably very expensive. There's a lot of uncertainty and sealing issues. We don't want the gas to come up from the aquifer and basically contaminate the water table. Okay. With that, I think we are going to move to the hydrogen role, UAE's role in hydrogen. We talked about Hydrogen Council. Now we're going to talk about this. So the National Hydrogen Strategy 2050 is set. This is actually a picture from the National Hydrogen Strategy from the website from the UAE Gov. And it does talk about 1.4 million tons of per annum of production of hydrogen, low carbon hydrogen by 2031, which actually is quite good. But and that includes one just green, which is basically from solar, and 0.4 blue hydrogen, which will probably use the gas. And the longer term targets are 2040, 7.5, which is actually again quite high, and 15 by 2050. So we're seeing that the hydrogen industry is really going to grow here. There are some examples. Dubai's Rashid Al Maktoum Solar Park that started around 2021. That is one of the examples for the pilot. And ADNOC building and ammonia production facility in Ruwais is another example in 1 million tons per year. That is about, the capacity is about that. Okay. So with that, I'm going to move to the my case study, which is what I did. I actually performed the sort of the work on this project. So UK hydrogen is industry is committed to have net zero by 2050, which is probably most of the countries saying that, and I think they've set this up in one of the COPs. And the central government is aiming to reduce the energy consumption by 2030 by 30%. So hydrogen was deemed to be a most important part, but last government change, there have been quite a lot of changes in that as well. So it's still not clear whether I think UK industry is actually a little bit behind on their hydrogen targets. So in terms of the work we did was that the hydrogen will be produced in Scotland, and the idea was that to store hydrogen in one of the onshore fields. Out of that, we actually look at some of the site selection of 10 depleted fields and aquifers, and depending upon the work, feasibility work, and the modeling work will be there, we will select one or two of them, which will go into the next stages. So it is a high-level feasibility work. And I actually used the software CMG Builder Gem, which was used. So on the left is just showing the generation, how much renewable capacity is there. Is about 35% of the renewable capacity is there. Now, if you remember previously, I mentioned about the energy balance. The solar, wind, and hydro are produced, but then they cannot be transmittable. So that's why, and not a lot of battery storage is available. That is why we are looking for some of the cheaper, buying the cheaper wind and solar to then convert into hydrogen and then pump hydrogen into the storage sites and then produce it when required. So in terms of electrolysis and thermal generation rates, for this study, we were looking at national grid. Obviously, it is connected to the national grid. Electricity is taken from the grid, which is used in electrolysis. Some of the numbers here, then taken into hydrogen storage, thermal generation, and then it goes from the site whenever you need. We are going to thermal generation and going back to the grid. So the idea was, today's presentation will not cover the entire study in terms of surface facilities and how it will be integrated to the grid. But the idea was really taking from the grid, making electrolysis, and then moving it to the grid. So these are the boundary conditions for some of the modeling work we did about how much power we are looking at and what should be the tons per day, because that is what we are modeling for. So for 100 megawatt watt, we were looking at 45 tons per day. That is the assumption, and 400 is looking at basically 4 times. Similar for the thermal generation. So it's about 4:1 efficiency ratio of electrolysis to thermal generation. So you can imagine that how much megawatt to megawatt conversion. So in terms of the study, we are starting with the screening of some of the fields, which is what we've started, building the models, looking at some of the history matching to make sure that the work previously done by the operators is correct. Then moving into some of the storage scenarios, trying to drill wells, very similar to how we do in the oil and gas developments. And then moving into the scenario building of how many wells, what are the rates, very, very similar to how we do in the oil and gas, where we are looking at what is the output and what is the input. So remember, the operator is trying to maximize the output by obviously doing some feasibility work in terms of cost, so to keep the wells to a low level, and trying to also see other things from the subsurface, like what is the impact on the aquifer or the permeability or some of the subsurface issues here, because we are actually storing it in a subsurface here, and we have not done that really for the pure hydrogen. We have been doing actually part of the town gas. Okay, so then we are looking at some of the risks, and then the project will then move into the, okay, how can we manage those risks? And then we are also looking at the facility. So and then this is the sort of cycle we were looking at. So in terms of sensitivity analysis, we are looking at different sensitivities of the key reservoir parameters like porosity, permeability, rock compressibility, relative permeability. And we will be doing that to test different things, like, for example, porosity, permeability for injectivity, storage capacity, withdrawal rates. Lithology, impacts, and cycle optimization are very, very important, because just like oil and gas, not one shoe does not fit all. It's very similar here. One field will show very different results, and it's very important to understand that. So in terms of the storage suitability, high one field simulation site was the one we selected out of the various ones, which we'll take in the next slide. We'll talk about what is important here, that the field should be able to have some storage capacity, decent storage capacity. And in this example, we had about 15 to 20,000 tons we were looking for. It's a smaller field, the feasibility. And then we were also looking at some of the injection withdrawal rates, about 300 to 200 tons per day, which we had to align with the grid scale storage requirements at the time. So obviously we need to know how much is the requirement at the time. Well placements, crystal wells we are looking at. So actually one of the well we were re-entering. So obviously the existing well was re-entered. Then we are also looking at some of the trade-offs: high rate, shorter cycles, but lower efficiencies, as in low rate, better containment. So lots and lots of sensitivities there. Those are important to do, and that is how we are looking whether we can do short cycles as well as long cycles for this field. And depending upon each field, that will also change. The operational optimization is also very important. So in terms of the 10 sites we looked at, there was depleted field, aquifer. Out of these, 4 went into the detailed study. Gas, aquifer, depleted field. Hello? So these are the different works performed. We did the full UHS feasibility work, and then key areas of study was cushion gas, looking at cushion gas requirements, well integrity, hydrogen performance, reuse of the existing infrastructure. Because one of the major reasons why we are thinking of this hydrogen storage in an existing depleted old field is to avoid the abandonment cost. So that is a key important thing. And the simulation model, we have created simulation gem compositional model on the CMG. In terms of the initial pressure, we had a decent pressure range, 250 bar, which basically means that we will be limiting that to avoid the leakage risk and relatively to the other screen sites. So we will see why. Okay, so one of the important thing in the simulation modeling is that we are keeping it a very simple model at this stage. So you can see it's a layer cake model. Now in oil and gas, it's very complicated because we want to model it very detailed. But at the very early stages, we actually do look at some of the layer cake models. And we were lucky to have some of the fields, actually most of the fields we've selected, we used a simple model approach of layer cake. Obviously the faults and everything is there. And we were using, why? Because we want to do lots of sensitivities, and we want to keep the runtime very, very low. So that was the reason why we did that. This is the porosity and the permeability, and you can see that the permeability range, for confidentiality reasons I can't say, but it's very good porosity and permeability in this field compared to some of the other fields where we looked at in the aquifer. There was low, and there was a sensitivity done in for permeability and porosity. Well, actually, I am displaying here. So we are looking at some 300 millidarcy, which is good compared to the aquifer. So why are we choosing high one? High one is chosen because it does behave like tank, making it suitable. We'll see in the next picture why. P by Z plot is straight, and it's got extensive data. So that is very important. And reliable simulation data for cyclic injection and withdrawal. Because remember that we are going to, if it's a small tank, then we will be doing a lot of cycling, which means withdrawing, injecting, and withdrawing, injecting, withdrawing. Okay, just a quick one on the pressure history, not going to the details, but this is the history and the model. And you can see a very, very good match here. And before conducting any storage feasibility work, we will be looking at this. So this is part of our storage feasibility workflow, which I've talked about. In this one, we can see that in 20 years, it does behave really well. Okay, in terms of the storage runs now, we will be looking at some of the sensitivities. Now, a key sensitivity is the new wells being drilled in that field, right? I mean, if it's onshore, the well cost is doubled. So onshore, it's a little bit less. So what are we seeing here? This is a plot showing gas volume going up on the y-axis with time. So this is an ideal storage single cycle plot where for this high one field where we are injecting, it goes up, then it stops, where the pressure actually reaches the initial the limit of the pressure which we have given for the cap rock, and then we produce, and then while withdrawing, we see that with uh, 1 well, 2 well, and 3 well sensitivity, we see the difference between the profiles of the withdrawal. And withdrawal is the most important because withdrawal is where we are promising our customers profile. So you can see here that 1 well, 2 wells is probably the best. 2 and 3 are exactly showing the same answer, which means that the maximum wells we wanted here is basically 2 and not 3. But actually, when we went ahead with the development plan, we went for 3 because we wanted 1 well as a backup.
Swati, just keeping in line with the time. So you would have around 5 to 8 minutes to wrap up, and then we'll follow by a Q&A.
Superb. Thank you.
Perfect.
Thank you very much. Then another thing very important here is to integrate the data to the surface and well models, because okay, we can actually do the subsurface, but what happens at the well? How is hydrogen going to behave at the surface? So actually, we use CoFlow well modeling, which is part of the CMG suite, and we were quite confident that this was hydrogen specific correlations are available, and they've done some good work as well there. And this was 3 years ago, and I'm sure there are more advancements now. So what do we see? We will be looking at, so on the left, we are looking at the rate versus time, the bottom hole pressure, tubing head pressure, and you can see it's hardly any difference. It's very small. Why? Because hydrogen density is very small. Actually, for some of the fields where we had aquifer storage, we saw a big difference. Why? Because of the water. So water is a clear no. We should not be producing any water here. We will talk probably more about methane. I mean, that's another topic that we will be co-producing methane. And you can see the gas rate profile here. Okay, so this is a typical sort of curve. The THP is important, reservoir pressure is important, but yeah, the surface facility, we had some idea when we were doing the feasibility study of some of the grid pressure, and we had to integrate that because the surface facility, designing that facility is important if hydrogen needs to be separated, especially in the case of co-production of some of the in situ gas. So in this case, we were producing actually some of the methane present, and for that we need some separation facility, and also that brings in its own challenges. Okay, so results and conclusion, I'm not going to go through each and every item here, but really the Hyven field can store 15,000 tons. This is what we can prove with the good rates, which is what was required for the requirement given to us by the customers of the hydrogen. And we did that by using this approach of integrating the data from the simulation to actually surface. And we looked at some of the risk management and caprock integrity, aquifer interaction, residual methane. We did look at some of them, but the next stage will be to look at further detailed work in terms of the rock interactions and some of the hydrogen specific surface facility upgrades and things like that. But what we can look at this stage is the big drivers: how many wells, study the cushion gas, which is basically a big capex item. And then we are also looking at, actually in this paper, we are looking at, which we'll probably see if you come in ADIPEC, we're talking about how we can actually apply the same to some of the UAE mature fields. Okay, this is a very quick one on the storage sites on the cost, which basically is showing that we can calculate a levelized cost of storage, and that will be looking at the capex, and then capex is very much dependent upon what kind of reservoir we are looking at, store we are looking at, whether it's depleted field, aquifer, and the main drivers will really be geology, depth, how much hydrogen is there, because if we are producing co-producing some of the existing fluids, then the cost of the removing of those goes up. So really the cost is a very complicated one. And what I wanted to say here is that it's a complicated one. And when we look at $3 per kilogram, things like that, that's a more on the production side. And again, that is very much dependent upon the electricity. And we talk about that because hydrogen as a fuel is directly compared to the fossil fuel. Okay. So I think I have finished here. I think there were a couple of slides in the beginning. I don't know if we have time, Abhijit, to go through.
Okay. Thank you, Swati, for that excellent presentation. We have covered a wide spectrum from hydrogen fundamentals to underground storage and the global trends. Now let's open the floor for a Q&A session. So I have some of the questions were lined up, and maybe I'll start with that. And in consideration of the time, we will be picking up one or two questions from the listeners. Yeah. So my first question is, what makes salt caverns more suitable for hydrogen storage compared to the depleted fields or aquifers?
Yeah, so that's a very good question. So salt, we're talking about a lot of salt caverns, but they actually can be ideal for their unique geological and physical properties, because it's almost like it's an empty space. So it's not there; they don't have any porosity, but they have and very low permeability, but very high seal integrity. Which prevents the leakage, because the hydrogen is, it's very important to understand the leakage here. Because of the lightness of the hydrogen gas, it is very important to understand that that is the biggest risk, especially if you're onshore. And so the purity of salt is ensuring that the hydrogen is remaining uncontaminated, unlike the depleted gas fields or aquifers, where you have a lot of residual hydrocarbons being produced at the surface, or microbes doing causing losses or reactions. So that is why salt caverns will be good. Additionally, salt caverns are also good for rapid cycling because they are much smaller. As we've looked at in that table we were talking about, they're much smaller. So hydrogen can be injected and withdrawn quickly because you need a confined space. So they are well suited for the short-term supply and demand and balances. So, on the daily cycles, especially in Europe, we have the supply and demand on a daily basis. It changes a lot. So that will be good. And the other advantage would be to use, they will use less cushion gas, which is basically the base gas to maintain the pressure, which is high in the depleted field. So compared to the porous media, the operational cost will be lower. But as we said, that the volume is less, and the initial cost of extraction of the mining the salt cavern is high.
Well answered, a bit long answer. Yeah. So my second question is in the high one field case study. So what key factors made it a strong candidate for underground hydrogen storage?
Yeah, so I think as I showed in my table, that we looked at about 10 fields, and 4 fields went to the next stage. So particularly this field was really good because it had one really important P by Z plot, which is basically used in looking at the gas. P by Z by GP was straight. So we could not actually find such a tank-like behavior. We call it in reservoir engineering tank-like behavior, which basically almost showing that everything is connected. I mean, it's not everything, but we really want to have a store where we don't have losses, and also we don't have compartments. So that is why it was important.
Excellent. So how did dynamic modeling help to validate the 15,000 tons of storage capacity at the high ones site?
Yeah. So the dynamic modeling is very important, and this I'm glad to actually have used. And now I think there are many dynamic simulation tools. We have all the standard ones in the industry, but really GEM was really good. And I think now since then they have really worked a lot on these hydrogen feasibility work, and because it's compositional simulation, which is basically not a black oil simulation, so you can actually have hydrogen specific specific reactivities, hydrogen specific physical processes being built. And it is very important because I was getting on a daily basis to check what are the withdrawal cycles, injection cycles from the commercial side as well to be modeled. So actually it was really crucial. And we were also looking at some of the geomechanical risks, depletion zones. We were also looking at the volume of hydrogen could be stored, but also cap rock integrity, because it's very important to understand that hydrogen is, if we are storing in the porous rock, sort of storage, then it should not leak. So that validation from the modeling really gave the confidence in our parameters and the overall strategy of this project.
Excellent. So since you talk about the P by Z plot, so what does the P by Z plot reveal in gas storage analysis, and why is history matching important in this context?
Yeah, so Kartik, P by Z plot is actually pressure over gas factor, which is very standard plot actually for using the gas in place behavior, P by Z behavior for the gas field. Now this is a gas field, so it's very easy. If it's oil field, it becomes a bit tricky, but it is a key tool which we use for estimating gas in place. And once we have that confidence of the store size, that was the first starting point. Now, because we already had a very good P by Z plot here, we were very confident to start with this high one. And we said, okay, we can go ahead, start work on this field, because simulation takes time, but P by Z really matching that data was helpful. And history match was easier because we already had a very good match. And a strong history match really gives us that confidence again in the predictive capability, which we were talking about before, about all the reliable estimates for the injectivity, withdrawal, cushion gas, and long-term storage performance. So yeah, it's really important.
Perfect. So how does the number of wells influence the injectivity, withdrawal rates, and the overall capex?
Yes, so number of wells, just like in oil and gas, are the main economic factor for any success of any project. Because what will happen is when we are producing a field, we can actually use one or two wells. But when we are constantly cycling, we want quick injection and quick production. So depending upon what is a profile we are looking at for the customers, we will have to drill more wells, even though we can still produce that field in one well. But we had to inject here, we had to put three wells here, one as a backup and two the main wells. So yeah, more wells will improve injectivity, which is what is needed, allows faster cycling. But each well will be adding to the significantly to the capex numbers, because drilling, completion, and again the facilities. So we have to be mindful of that balance of drilling the number of wells versus the capex.